So, in the last lecture, if you remember, we spoke about integration, which is path independent. If it is path independent, then it is possible to calculate something far away from the crack tip and still know what is going on at the crack tip. This gives us the advantage of doing a test and using this formulation to get the information relevant at the crack tip. If you remember, the J integral had a mathematical description at the crack tip, which was the strain energy density integration along the y direction. So, this is x, this is y, and we are dealing in 2 dimension. This whole idea was also invented or applied because this kind of formulation already existed in other domains of energy. So, in electrical energy and in magnetic energy fields or in any other conservational energy field, we had this kind of formulation already, which was applied by James Rice in fracture mechanics. And so, you have strain energy density integration in the y direction minus traction vector into del u by del x ds. ds is a small portion on the contour. Contour goes counterclockwise and u is the displacement and x is the x direction. Okay. So, what you can do is you can try calculating this for a very simple path. So, you take a path which goes like this. Okay. So, you calculate for this path, or even a simpler one will be, instead of having a circular path, you can have for a crack like this, you can take a path which is like this. So, of course, here we are excluding the crack tip. So, if you do this, if you do the calculation for this one, then you will find out that the integration value is 0. So, J integral will be 0 if you do not have a crack tip in the contour. Okay. You should check this to see if it is 0 or not, and you should also see if what happens if you find out the integration clockwise and counterclockwise. Okay. So, you do not need to know the values of stress and strains. You can just assume that this sigma is the value of stress and epsilon is the strain, and then rest of the things will follow. For practice purpose, you can there can be a derivation where this integration value is provided for some simple paths, and that I will provide for you to understand. So, at this point of time, this concept is a mathematical integration. The question is, how do we find out experimentally the value of this? So, let me go to the next. So, James Rice, who described this integration, also proved that this J integration can also be measured experimentally because it tells you about a pseudo strain energy release rate. So, maybe this term sounds familiar to you because the same concept was given by Griffith, which was strain energy release rate, which was G in Griffith's calculation, and the symbol G because he was Griffith and J because James Rice. And so, Rice proved that J is equal to G with some correlation. So, but the difference is G will only work, it only worked for brittle material. J, however, we will see that it works for elastic plastic material also, although theoretically it is invented or discovered for non-linear elastic material behavior. So, what J integral does in its heart is that it is assumed that the material follows deformation plasticity. Deformation plasticity is a theory which works only in monotonic loading. So, as long as you are going in one direction, so this is the stress strain curve for metallic materials will look something like this. So, as long as you are just pulling it, just loading it, so as long as you are going in this direction, this theory, the J integral is applied, there is no problem. Okay? But if you unload it, or if there is some amount of unloading which usually happens after ultimate tensile strength, and it may also happen in a compact tension. So, in the specimens of fracture mechanics testing. So, if you have a crack in the system, you might have unloading even when you are pulling the specimen. So, if you remember, this is my CT specimen, and let us deal only in 2 dimension. So, what happens is you are pulling this. Okay. So, each point in this material, each point in this specimen is a material point, right, and those will follow this stress strain curve because the material is same everywhere. So, if you take a point there, will behave in this way, if you take a point there, will also behave in that way. So, they are, because it is the same material, it is going to follow the same stress strain diagram wherever it is. Okay. So, what happens when there is a crack growth? If the crack grows, then this much amount of crack surface has opened up, right. So, initially you had this much of the material under tension because that was getting pulled, but now you have only this much amount of material which is under tension, right. What has happened to this much amount? That amount of material, because the crack has opened up that surface, what has happened is that part has unloaded, that part is now stress free, there is no load on that, right. That is a kind of unloading because that part was actually loaded at a higher stress and then you unloaded it, right. And we know that at crack tip stresses are much higher than yield strength. So, obviously, you have some amount of plasticity at the crack tip before crack would grow, and once it has grown, this area which was before at the crack tip, but now it is free of surface, has plastically deformed. So, we are somewhere in the plastic region, right. So, and then it has become stress free. So, it means it has unloaded. When you unload this, it does not go back like it would according to the assumption of non-linear elasticity. So, non-linear elasticity simply means that the elasticity is not only linear, but it is also non-linear. So, this concept was used by Rice to define J integral. We will answer that question, that why this concept was used, but at this moment just understand this, that the J integral concept was developed thinking that the material is deforming elastically, but it follows this path which is non-linear, right. That is why it is called non-linear elasticity. Why it was done? Because metallic materials and other materials, almost all materials except if they are very brittle, they usually deform plastically, right. So, if you have a plastic deformation, that is obviously not linear, but you cannot entertain a irreversible phenomena if you want to put something like J integral in the application. So, Rice assumed that the material is deforming elastically. What would it mean if I say that this whole thing is elastic? It would mean that when I unload, it will take the same path and go back to zero strain, right. Elastic deformation means it is recoverable, it is reversible process. It is a different question if it is linear or non-linear, but if it is elastic deformation, once you unload, it will take the same path back and it will go back to zero strain. But in reality that will not happen. It will unload and only this part will be elastic recovery, right? And this is where there is a problem in J integral, and we will discuss that part also in a little detail. But at this point of time, it should be very clear to you that this assumption was made by Rice. Now we come to that question, that why this assumption was made. Why Rice or anyone who works on J integral cannot entertain a plastic deformation. So why can we not assume this deformation as it is in reality and still work with J integral? The problem is this, that our theory that the integration of any force is 0 and plus minus if you have a source or sink is equal to 0. This works for a conservative field. What is the meaning of conservative field? So this is an idea from physics, and we have discussed that it works on gravitational energy, electrical, magnetic, electromagnetic energy, any energy field which is conservative, it works there. Okay? Not necessarily energy, but anything which is conservative, meaning that it is not dependent on the path taken, but it is dependent upon where you are. Okay? So that's why, so this assumption says that as long as f is conservative, you can apply this. If it is not conservative, meaning if it is path dependent, then you cannot apply this, right? And that is the problem. So in plastic deformation, so if I say that this is, I have a non-linear elastic deformation. So if I am here or here, it does not matter what path I have taken. If I unload, I will come back to that, right? So if I have loaded it like this and I went to that point and then I unloaded it, okay? So it does not matter that if I load it or unload it, it will be at the same point. But in a plastic deformation, if I unload it, it will not take the same path. So at the same stress, you can have two different strain values depending upon if you are loading or unloading. So it is path dependent, the plastic deformation. Elastic deformation is not, but plastic deformation is path independent. So this is not a conservative field, and that's why it is not valid to apply J integral. In plastic deformation, partially true. You can apply J integral in plastic deformation if you are not coming back, if you are not unloading. If you are just going in this direction, you are still in conservative field. Okay? So for each stress value, you have one value of strain, right? So J integral is valid. As soon as there is an unloading, you have a problem. You have a non-conservative field. You have two values for one stress value, two strain values. So there it is not possible to apply J, and therefore it is theoretically not possible to apply J integral in fracture mechanics, because you will always have some amount of plastic deformation. It has to happen there, because at the crack tip stresses are usually, even if it is a circle which is a very blunt crack tip, for that also we have seen according to English formulation that it is at least 3 times of the applied stress at the crack tip. So sigma at tip is at least 3 times of the yield strength. So obviously there has to be some amount of plastic deformation, and therefore we cannot apply this. But if we assume monotonic loading and no unloading, then we can still apply this. Okay? And this was assumed that we don't do that. We don't do unloading, and so we can apply this. Now if we imagine that we can apply this, then Rice proved that J is the rate of change of strain energy per unit crack length. Okay. And this is same as Griffith's energy, which is same as stress intensity factor divided by elastic modulus. This dash is for plane stress and plane strain condition. You will have to change E will be equal to E in plane stress, will be equal to E by 1 minus mu square in plane strain. Okay. So, it represents both. So, this is the correlation of Griffith and stress intensity factor of Irwin and Rice's J integral. Okay. So, it gives enormous amount of advantage. One advantage, you measure anything at the remote location and you know what it is, because J is path independent. So, you are getting the force value from the machine here, you are getting the displacement value from the actuator or from a device which is at the crack tip. Using those data from the experiment, you can calculate this, and that part, how do we calculate J integral experimentally, we are going to discuss in the next page. So if we do the experiment, and that we have discussed before, that we do the experiment in the same machine, we have discussed about the specimen, how they are loaded, how do we get the information. So, what information you basically get from fracture mechanics test is the force, which is usually in Newton, you can put it in kilonewton or whatever, and displacement in millimeters. We can get it in micrometers if we are working on a very miniature specimen, but we will never get it in meters unless we are doing the test for a very large specimen. But even then, displacement usually is in millimeter dimension. So, for metallic materials, you will get something like this. It will look like stress strain diagram, but it is not stress strain diagram, it is force displacement value. And as soon as crack growth starts, the curve will start going down because the ligament length is decreasing. The material which is holding the two parts up and down the crack tip, that part is decreasing as the crack grows, and that is why the force decreases. I hope you understand that part. So, if this is my cracked specimen and I have this much part which is connected. Now, as crack grows, that part is decreasing, right. So, initially you can imagine that there was a thick material which was holding, and now you have a thinner material, and with crack growth this part will be decreasing, right. So, thinner and thinner material is holding the two parts, and therefore, the force is not required that much. So, force will decrease as the crack grows, right. So, this is what you get from the force versus displacement curve, and J integral tells you something unique about a stationary crack. Okay? That part we know, because as soon as crack grows there is unloading and J is not applied, J is not valid anymore, right. So, but we know that if you do testing of this crack length, let us say this is the crack length of A, and then you take another specimen in which you have initial crack of, let us say, A plus delta A. Okay. So, for these two specimens, the value of J integral will be different, because the size of the source of energy, the singularity, has changed, right. So, because we have two different singularities in the system, two different defects in the system. Defect is crack we are calling as a defect in this case. So, we are not talking about microstructural defects. So, the singularity crack, we can call that also as a defect. So, there are two different defects, right, because the geometry will be different if you have different crack lengths, and therefore, the value of J will also be different for these two cases. One case with a crack length of A, another case with a crack length of A plus delta A, and J describes this difference in the energy. Okay. So, if I have two different specimens and if I take the force, if I do the testing for, let us say, a crack length of A, so the load displacement diagram will look like this. Okay. So, initially some linearity and then non-linearity, but you do not have any concept of yield strength and all those things here. Okay. So, do not think about the stress strain diagram kind of behavior in this case. Although the initial linear curve comes because of the elastic deformation, but it has nothing to do with the yield strength and all those things, because at the crack tip you will already have plasticity even if you are there. Okay. So, this is the force displacement curve of the total specimen. It is not local at this point or that point, it is coming from the machine. So, it is the total force applied on the machine and total displacement of the specimen. Okay. So, the displacement by which it is opening up. So, this is the diagram for crack length A. So, that is A, right, and then I have a higher crack length which is A plus delta A. So, of course, the force will be much smaller than that, right, because the less area is holding the material. So, you will need less force to deform this. So, the force displacement curve for A plus delta A will look like this, right. Now, you stop this at a fixed displacement value, and therefore, this area so area under this curve is a form of can be related to energy, right. So, this area difference in the area. So, if you have, for instance, loaded material which has initial crack length of A, then the total energy will be this, and if you do the same thing for a crack length of A plus delta A, then that will be this, right. So, what is the difference between these two is this part, right, and this part can be given as J B d A. Okay. So, J you can then tell as the area difference between these two divided by B into delta A. So, J actually is the energy per unit thickness per unit crack increment. Okay. Right. Now, from this concept we will try to understand how can we calculate the experimentally we can calculate the J integral. Okay. So, we can do a little bit here only. So, as we do the experiment, so consider this one, because we are still dealing with single crack length specimen and we do not want the crack to grow, because if it will grow then J integral is not valid. So, what we will do is, and we want to know how J value changes at different crack lengths. Okay. We want to know that. So, what we will do is we will do the testing at different crack lengths. So, we will make 10 specimen, right, and serial number 1 specimen will have a initial crack length of, let us say, 10 mm. Then we will take specimen number 2 and we will do it at, let us say, 12 mm, and then we will take specimen number 3, we will do it at 15 mm, and so on, and we will have J integral value for different amount of crack lengths. So, then we can calculate it as delta A. So, initially we will say that delta A is 0, then we will say that delta A is 2 mm, then 3 mm, and so on. Okay. So, at the end we will get the behavior of J integral with increasing crack length, and that is what we want to know. and we will discuss why we want to know that. Okay. So, what are we doing? We are doing this testing. Okay. So, at a stationary crack we are not asking the crack to grow, and then Rice again gave the formula by doing some calculation on 3-point bend specimen. So, SENB type of specimen, if you remember. So, we are bending this specimen which has a crack in 3 points, and for that J integral can be given as 2 into area under the curve divided by the thickness of the specimen into the ligament length, right. So, you see, instead of delta A we are using ligament length, and delta A we do not have here because the crack is not growing in this case. Okay. So, crack is not growing. So, you get this curve, and then you know the area under the curve. That area under the curve is A, B is the thickness, right. So, area under the curve is what? Force into displacement divided by B into B. So, B into B is area, force divided by area is stress, stress into the displacement, right. So, that will give me energy per unit some displacement, right, because stress into strain, if you remember, stress into strain in energy per unit volume, but here it is equivalent to stress into displacement. This is not a strain, right. So, there is a dimension missing. If I have something down here, then that, so let us say the dimension of displacement is millimeter. So, I want something in millimeter down, so that can cancel out, and then it will be equivalent to energy, right. So, in this form it is still not energy, it is energy into some dimension, right. So, that dimension is crack length. So, I have to find out what will be the case if I have different amount of crack lengths, and that I will get by doing this testing. So, I will have to test a lot of specimens to find out the value, right. So, for a stationary crack, J was described as this, and this is for 3-point bend specimen. If you do the testing on CT specimen, then J was described to be 2A into B and then 1 plus alpha divided by 1 plus alpha square, where alpha is again, if you remember our stress intensity function lecture, then there we had a function of f of A by W. Similarly, alpha is also a function of f of A by W, where A is the initial crack length, W is the thickness of the width of the specimen. Okay, so that geometry factor is coming. And why geometry factor is coming? Because CT specimen is geometrically different from SENB specimen, and that is why it is, this factor is there. Okay. So, these formulas, the derivation is not important, because, well, you can see the derivation, but that derivation is not required at this point of time, because that requires a little bit more knowledge about bending and stress and strains in that situation. So, we will skip that part, and what is important here is that you can find out J integral experimentally by finding the force and displacement of the specimen. So, you get the area, and this area is telling you about the energy which is consumed in deforming this material. Okay. So, that is how you calculate the energy release rate. Now, look at it in that way also. Okay. So, for a crack length of A, as long as this A is not growing, this is the area which is, this is the energy which is consumed by the specimen, right. If the crack grows to an amount of delta A, then this is the energy which is consumed by the system, right. So, what is the energy release rate? By what rate the energy is being released, you can find out by the difference divided by delta A, right. Difference in these two divided by how much amount of crack length has happened, and that is what we are trying to do. Okay. So once you get this value of j at different values of crack lengths, then we can plot that. So that we will do in the next page. So let us say we have done those testing of 10 specimen, and at different crack lengths we have obtained the value of j, and now let us plot those values. So let us say so initially you will have something at 0. So you will have some data point which may start here. So j will have some value there, then you might have some value there, then you might have some value there, then something here, something there, something like this. So if you happen to join this, then it looks like this. This is how j delta a curve looks like. Okay. So at different value of crack lengths you have, so you have done how many testing? 1, 2, 3, 4, 5, 6. Then of course you have done 4 more, but that is not relevant. So that's how you get these points. So these 6 points actually indicate 6 different tests performed for stationary cracks. Alright. So now the standard definition of how do you get the fracture toughness of the material. So far what we are plotting is energy release rate as a function of crack length, okay, crack extension. So now what is fracture toughness? If you remember our stress intensity factor definition, then we had a parameter which was K1C, which was the critical value of a stress intensity factor required to initiate a crack in mode 1, right. In this case we also have something which is called J1C, because we are testing in mode 1. So it is J1 critical value, which tells you that now the crack has start propagating. How do we get that? Do you think this is that value? No, it is not the value beyond which there will be delta A, although from the plot it looks like it. But what happens in a plastic material is that initially you have a very sharp crack tip. It will never look like this, it will always look like straight line, okay. But if you look under a microscope, you will obviously have some gap because that part has separated. And also for understanding, we should, I cannot explain on a line that there are two surfaces. So in reality it will not look like this, but this is a very sharp crack, okay. A sharp crack will look like that. So this is a very sharp crack, and